This is Physical Science 2, Chapter 26, Part 4 on Stars and Galaxies. In this portion of the video lecture, we will be discussing the study of the universe known as cosmology. So cosmology is the study of the universe, how it formed, how it continues to expand, how it changes over time. Do not get this confused with cosmetology, which is the science of doing hair and nails. Some early theories about the universe formation, probably the earliest of all theories, which was proposed during ancient Greek and Roman times around 2 to 10 BC, is called the steady state theory. This theory states that the universe has just always existed. Being that in ancient Greek and Roman times there was not an entire catalog of vast scientific knowledge like we have today, so that was really the best way to explain how everything got where it was. Simply saying it has always been satisfied peoples for quite some time. The oscillating theory developed quite a few thousands of years later. The oscillating theory works in the way that the universe will expand very rapidly, and then it will hit kind of a point of maximum expansion, and then it will start to contract. And when it contracts, it will get to a space so small that it will then start to expand. And it kind of starts going back and forth, much like an oscillating fan. When you turn on one of those, it starts at one side of the room and then sweeps all the way over to the other side of the room and back again. Or like a yo-yo, this back and forth, or like an accordion. The universe expands, contracts, expands, contracts. The most widely accepted theory of universe formation is what we call the Big Bang Theory. Now, there are some misconceptions as to what the Big Bang Theory is. The Big Bang Theory is not an explosion of all planets, asteroids, moons, nebula, stars, all of that stuff. It's not just an explosion of matter into empty space. The Big Bang Theory explains how space itself expands. So the Big Bang Theory is the rapid expansion of space and how to explain that. So when did we start? As far as we can tell, the most accurate age of the universe that we can get is around 13.7 billion years old. There is some evidence that supports this idea of the Big Bang Theory. So there's kind of a product that's left over from the initial expansion. And we call that cosmic background radiation. This is still energy that was left over from the original Big Bang event. Cosmic background radiation is kind of like the white noise of the universe. It's present everywhere, and we can still detect that. So again, cosmic background radiation is evidence that supports the Big Bang Theory. We can also show that the universe is still expanding today. We can take the motion of the stars in our own galaxy and figure out where they're going with the Doppler effect. Doppler shifts occur in light waves. They also take place in sound waves as well. Now, don't get this confused with like Doppler weather radar. It's a little bit in a different context than that. Doppler shifts in light and sound because light and sound travel in waves. And so if that light or sound is moving toward you or away from you, it will behave differently. Doppler shifts in sound waves. I'm sure you've all had the experience where you've been on the street and an ambulance is coming down the road or a fire truck. The fire truck or ambulance sounds really high-pitched and kind of whiny sounding when it's coming at you, and then you can hear the pitch of that siren tone drop as the ambulance or fire truck drives away from you. So it's higher sounding when it's coming at you, and it's lower sounding when it goes away from you. That's because that sound is moving, and as the siren is putting its sound out in all directions, those sound waves are compressed at the front of the siren, and that gives that sound a higher pitch. When the sound is moving away from you, those sound waves are stretched out and they're spaced apart further, so that pitch sounds lower. Now we can apply this to light waves as well. So we can detect the movement of a star based on what its light waves are doing. So if a light is moving towards us, those wavelengths of light are going to be compressed and they'll appear shorter, meaning that they're going to hit your eyeball at a faster rate. If you're on the other side and the light source is moving away from you, those light waves are stretched out, and so they will hit your eye at a slower rate. So it will appear differently than moving towards you. So if a star is approaching Earth, those light waves will be compressed, and we call that star in a blue shift. Blue is the shorter end of the visible light spectrum. Now this is a false color image. These stars don't actually blink bright blue, but we can use a spectroscope to detect that blue shift movement. Now, if a star is moving away from Earth, again, those light waves are going to be stretched out, and so we say that that star is in a red shift and it's moving away. Again, a false color image, but we can use those spectroscopes to detect that very slight movement of stars. So if a star is moving away, it's in a red shift. If it's moving towards you, it's in a blue shift. Now, when we take Hubble and we look out into what we call Hubble Deep Field, which is the image that you see here, each one of those specks of light is not a star, it is actually an entire galaxy. So what Hubble shows is that galaxies and things that are outside of our Milky Way galaxy all have a red shift, which would mean that all of these galaxies are moving farther and farther away. So this accounts for everything that's happening outside of the local group. Remember, the local group is our little galactic neighborhood. It's about 45 galaxies, including ourselves. Outside of that, things seem to be expanding still to this day in a red shift. So what's in the universe? There's a lot of things that we can see. We can see nebula and stars and planets and moons and comets and asteroids. So visible and detectable mass is a very small part of what the universe actually is. When you think about it, from the perspective of our solar system, the closest star in our solar system, of course, is our sun. And we have all of our 8 planets orbiting around our one sun. So what is in that space of space? That's what astronomers and cosmologists are trying to answer. So when we think about the distances between solar systems, between galaxies, what's there? At this time, we don't have the technology to be able to detect this matter that we don't know about. So we call this matter dark matter, only because it's unseen and unknown to us. You can think of the dark matter as the stuff that makes up the space of outer space. It's the unseen matter of the universe. If we could somehow get above our whole entire universe and take a picture of everybody, and see where the visible and detectable matter is, galaxies would form in very high density regions. So in the whole universe, there's these big voids, there's these big spaces, and that's where we believe that the dark matter is. It's that stuff that makes up the space of outer space. So when we say that the universe is expanding, how is it doing that? Again, we can detect forms of energy such as heat and light and sound, but we can't detect the driving force behind this expansion. So we call this dark energy, believing that this is causing that acceleration of the expansion of the universe. The science of cosmology has a lot of questions to answer, but the more that we understand about how planetary systems form, how galaxies form, we can kind of understand our whole place in the universe. This has been Physical Science 2, Chapter 26, Part 4 on stars and galaxies.